Hello everyone, and welcome back to some more remote learning. In today's example video, we're going to go over Newton's method. Now, Newton's method allows us to approximate roots of a function, which is pretty helpful to know, which we'll see in these next couple of examples. And we can approximate those zeros simply by repeating a single formula. Let's look at that formula below and how to use it for the function x cubed plus 2x squared minus 1. Now I said that formula is used repeatedly, so we're going to use it multiple times. But what we plug into the formula is going to be slightly different each time. And that's because our output of our formula is our x sub n plus 1. And what we use in our formula is all that previous term, x sub n. So x sub n minus our function value of x sub n all over the derivative at x sub n. So taking that x value, subtracting its function value over its derivative value, that's going to be our new x value. So when we get that new x sub n plus 1, well, in order to get the next x sub n plus 1, that then becomes our new input. But where exactly do we start? Well, our x sub n, our very first option, we want it to be somewhere close to the root. So in this example, I already have a couple x sub n's, my x sub 0, my starting value. You can see I have some root over here. So I guessed around negative 1.75. Here, it looks like my root is negative 1, so I guessed negative 1, or I estimated negative 1. And here it looks like it's around 0.6 maybe, so I'm going to estimate 0.5 and use that starting value as my x sub 0. And when we plug in x sub 0, x sub 1, plugging in 0 for n, x sub 1 is going to be x sub 0 minus f of x sub 0 all over f prime of x sub 0. And you can see that x1 output is going to be my input for x2, because in order to get 2 here, I need to plug in an n value of 1. So then I'm going to have x sub 1, my previous output, minus f of x sub 1 all over f prime of x sub 1. And then I'll use my x2 as my next input to get x3, and so on. So you can see that this same formula, that same pattern, is repeated multiple times. So now that we know how to choose a good x sub 0 value, something close to what looks like our root is, we know now that we just repeat the formula, but when do we stop? We stop when the formula starts outputting the same exact value as it previously did. So let's take a look. Let's estimate this first root here. So I'm going to say my starting x sub 0 is negative 1.75. So my x sub 1 is going to be equal to x sub 0, negative 1.75, minus f of negative 1.75 all over f prime of negative 1.75. And again, since this formula is repeated, we're going to use the same function to plug values in, and we're going to use the same derivative to plug values in. So feel free to get out your calculator, but what I recommend is actually using some sort of tabular program such as Excel. So let's go ahead and pull up an Excel sheet to see how these formulas develop. So here I've gone ahead, I've zoomed on into my Excel spreadsheet. Now my x sub n, remember, for that first root, we said it was approximately negative 1.75. So I'm going to type that in. Now remember, my formula is x sub n minus my function value at x sub n all over the derivative at x sub n. So I'm going to use x sub n minus f of x sub n all over f prime of x sub n. So just to keep things in line, I'm going to go ahead and rewrite my function value and its derivative. So remember, our function was x cubed plus 2x squared minus 1. I'm just going to write this just so you guys can see it visually on this sheet. Now the derivative of that would be, well, the derivative of x cubed is 3x squared, and the derivative of 2x squared is going to be 4x, and then the derivative of 1 goes to 0. So there's my f of x, and here's my f prime of x. Now what I'm going to do is I'm going to apply those using my cell values in Excel. So I'm going to say equals, remember my formula, x sub n, so I'm going to click that previous cell B2, minus f of x sub n. So I'm going to put this in parentheses, and I'm going to say my cell B2 cubed plus 2 times B2, that quantity squared, minus 1. So there's my function value of my cell B2, and I divide that by my derivative at my cell B2, that value of negative 1.75. So then I'm going to have, again, parentheses, 3 times B2 squared plus 4 times B2. And go ahead and hit enter, and you can see my next value I get is negative 1.64286. So that then becomes my new x sub n. So if I click this and drag down, because we always use that previous cell, the formula will transfer through. So x2, when this is calculated, you can see that that formula used the cells from B3. And I can continue to drag this down. So for my next cell, I'll use that previous one and so on. And I can continue to drag this down. And look, when I get to my x sub n of 4, I'm at negative 1.61803, and that continues on. So you can see right after that starts repeating, I know that that's going to be my same value. So let's go ahead and copy these values directly over to our table. So for negative 1.75, remember my x sub 1, that first value was negative 1.64286, and then my next value was negative 1.61921, and then x sub 3 was negative 1.61804. Then when I got to negative 4, that's when I found my value and started repeating, that negative 1.61803. So it's safe to assume that that negative 1.61803 is the x value of my root. That was pretty close to negative 1.75. Now we're going to do the same exact thing for that negative 1, because negative 1 looks like it would be my next root. So I can go to Excel and use that table, but since this is a whole number, I think this is going to be a good one to start with doing out by hand. So x sub 0 is negative 1, so I'm going to find f of negative 1 and f prime of negative 1. So x sub 1 is going to equal negative 1 minus my f of negative 1. Negative 1 cubed is negative 1, plus 2 times negative 1 squared is 2, minus 1. You can see that I have negative 1 plus 2 minus 1, that's going to give me 0. So I don't even care what my denominator is, because I know this is overall going to be 0, but let's quickly solve for it. Remember that was 3x squared plus 4x. When I plug in negative 1, I'll get 3 plus the negative 4, which is going to be 3 minus 4, which is a negative 1. But it doesn't matter because this goes to 0. So my x sub 1 is equal to negative 1. But wait a second, that's exactly what we had previously. So then if we tried to enter negative 1 in again, we would get negative 1, and we would continue to get negative 1. So actually, our guess was right on the root. That root is negative 1. So when we're at an x value of negative 1, our function value is 0. And then the last one we're going to figure out is, well, we already have the negative 1.61803. This one right here was an x value of negative 1. Next, we're going to estimate the one that's close to 0.5. And let's use Excel for this. So we're going to pull up that table that we previously created. And all I have to do, because I'm using the same exact function and the same derivative, I just have to switch my starting value since I based everything on the previous cells. That's the nice thing about using a tabular program. I'll just enter in 0.5 and hit enter, and then it will adjust all my values. So you can see that this actually starts repeating at the third one. That's when it starts, and by the fourth one it's repeating. So 0.618034 is where my next root occurs. But let's go ahead and fill in that table. My x sub n, where n was 0, was 0.5. Then I used that 0.5 to get my x sub 1, which was 0.636364. And then after that, I got 0.0618382, and then 0.618034, and then the very next one, it started repeating. So I don't even need to fill in those rest of the values. I know that this is going to be a root of 0.618034. So filling this out, 0.618034. And that's how you find the roots using Newton's method. So now that I've showed you that tabular method, we'll just continue using this. So now that we've found both our roots, I want to quickly note one of the potential mistakes that could happen. And that's choosing an inappropriate x sub 0 value. And sometimes you're going to think that you have a pretty good value to help you estimate, and it's not going to work out. So you always want to double check this. So for example, let's say I was trying to estimate my root that we know is -1. And let's say I use the value, well, I want to use the value over probably towards this negative side, but let's use some value over here, like -0.1. Okay, so we're technically pretty close to that, but let's see what happens when we use -0.1. Let's go to that Excel spreadsheet. The root I'm trying to find is -1, but look what happens. When I enter in -0.1, what root does it give me? Well, all the way down here it starts repeating. It gives me that farthest root, that -1.61803. So even though this was closer to that -1, it completely skipped over that root. So this is one of the common mistakes that can be made. So just double check your work. Maybe try another x sub 0 value just to make sure that you're getting that appropriate root. But I thought it was good to note this so that you guys are aware. But let's continue on now from this to example 1. So scrolling down to example 1, well, we're not finding the roots in example 1. It wants us to find the maximum and minimum values of that same exact function from up above. But remember, Newton's method helps us approximate roots, approximate those zeros. So for min and max values, that's when the derivative equals 0. So as opposed to using g of x, that's x cubed plus 2x squared minus 1, we're going to use g prime of x. So we want to figure out our roots for 3x squared plus 4x, which if we scroll back up above, that maximum value looks to be at, well, let's say that's about -1.4. And this one looks to be right at 0. That looks like the max, and that looks like the min. So let's go ahead, use Newton's method, using the derivative to plug values into the formula. So again, my starting value for that maximum, I'm going to guess to be around -1 point, let's say 1.3. And then the next one, I'm going to guess to be at an x value of 0. That's where I believe my max is, and that's where I believe my min is. So using those as my x sub 0s, my x sub n plus 1 is going to be x sub n minus, what's my f of x? That's going to be my g prime of x. So I'm going to use g prime of x sub n all over its derivative. So g double prime of x sub n. So I know my derivative is 3x squared plus 4x. So my second derivative, if this was f of x, here's my f prime of x, that's going to be 6x plus 4. So let me go ahead and write those functions in to our Excel spreadsheet so we can use them, and that way we don't have to keep referencing our worksheet in case you don't have two screens when you're working on this. Our function now is that derivative, so I'm just going to copy what we originally had, and then we're using that second derivative. That's going to be our f prime of x. So that was 6x plus 4. And again, I'm noting this just to make writing the derivative easier. So I'm going to delete all these cells here, and I know that my x sub n value that I'll start using is that first one, negative 1.3. So negative 1.3, using that, I'm going to write my formula. So this is going to equal x sub n, the previous cell, minus f of x sub n. So my function values, that's going to be, making sure I have it in parentheses, 3 times the previous cell squared plus 4 times the previous cell, all over the derivative using that previous cell value for my x. That's going to be, making sure it is also in parentheses, 6 times that previous cell plus 4. All right, so my next value is negative 1.33421. Dragging this on down, it starts repeating pretty close. So after I get my x sub 2, then it starts repeating. So this is negative 1 and 1/3. Let's go ahead and fill that table in. So using that value of negative 1.3, then the next x sub 1 was negative 1.33421. And then next it was negative 1.3333, so negative 1.3 repeating. So that is where our maximum value occurs, that negative 1.333 or negative 1.3 repeating. That's where that maximum occurs. And if we scroll up on the worksheet, you can see, yeah, it does look like negative 1 1/3 where that maximum value is. And the other one looks to be right at 0. And let's confirm that. So going back to Excel, as opposed to my x sub 0 being that negative 1.3, I'm now going to guess 0. And look, it is indeed 0. So going back to our worksheet, we can fill in that table. Because we get 0 for the next value, we know that the minimum does occur when x equals 0. So that's another way we can use Newton's method. We can use it to find the roots of the derivative, which will tell us the mins and maxes of our original function. And another way to use Newton's method, we're going to, in example 2, calculate the point where the function x over 2 and our function x squared minus 1 intersect. So remember, when two functions intersect, that's when their function values are equivalent. So I'm going to see when x over 2 is equal to x squared minus 1. But how can I use Newton's method? Remember, Newton's method helps me find the roots, so I just have to figure out how to have some function equal 0. So I'm going to say that 0 is equal to x squared minus x over 2 minus 1. This is my function value that I'm using. So if that is my function value I'm using, then that's derivative is going to be 2x minus 1/2, and then 1 goes to 0. So I'm going to use my function of x squared minus x over 2 minus 1 and my derivative. And what would be a good estimation for those intersection points? Well, we can plug in points and kind of get an idea of how the function is shaped, or what I've already done is I've graphed it out. You can see here is my x squared minus 1, and here is my x over 2. So a good estimation would probably be around negative 0.75 for this first intersection point, and the second estimation would probably be around 1.25. So I'm going to use those as my x sub 0 to find those intersection points, because what we currently have is x squared minus x over 2 minus 1. You can see that those roots are indeed aligned. When that red function intersects the x-axis, that's where the intersection point occurs, and where the red function intersects the x-axis over here, that's where my other intersection point occurs. So let's go to Excel and attempt to find those roots using the values negative 0.75 and 1.25. But before we jump to Excel, again, remember those values we are going to use to estimate our roots is negative 0.75 and then 1.25. So I'll write those in really quickly. Negative 0.75 and positive 1.25 were good estimations for our roots. So now let's move on to Excel. So our new function value we said was x squared minus x over 2 minus 1. So just writing this so I have a reference, then my derivative was 2x minus 1/2. So the first value I'm going to estimate for that intersection point was negative 0.75. Now I'm going to enter in my formula. X sub n minus f of x sub n, which is b2 squared minus b2 divided by 2 minus 1, and that's all over my derivative, 2 times b2 minus 1 over 2. Closing that parenthesis, my next x sub n value would be negative 1.01. Continuing this on, you can see that I start repeating right around that fourth value at negative 0.78078. And this should have said a negative 0.75. I accidentally typed in negative 1.75, but you see it doesn't make a difference because I'm going to get that same value even though I accidentally had the wrong number typed in. That's okay because that was still relatively a close value in the grand scheme of things. But when I use the other value I wanted to use, that negative 0.75, you can see that that value of the root doesn't change. So let's go ahead and fill that table in now. So after negative 0.75, we got negative 0.78125. And then from there, that's when we started getting our repeated value of negative 0.78078. And then that repeated. So that first root, or in this case, our first intersection point, is negative 0.78078. If we were to plug that value in to f of x and our g of x, you would see that those give the same exact function value. F of x will be equivalent to g of x at negative 0.78078. Now, let's find that next intersection point using that x sub 0 of 1.25. So all we do is switch our x sub 0 value because our function and derivative are the same. So entering in the value we want, that 1.25 for our estimation, you can see we start repeating for 1.280776. So that x value is where our original functions intersect, which is the root of that manipulated equation when I set them equal to each other. So filling in our table, finishing this worksheet out, we'll have 1.28125 was x sub 1, then 1.280777 was x sub 2, 1.280776 was x sub 3, and then that's where it started repeating. So again, that intersection point is 1.280776, that x value. If I wanted to find the y value, I can plug it into either equation because it's going to give me an equivalent function value for each. But those values are where my two given functions intersect. So hopefully from the examples in this worksheet, you realize the value of Newton's method and how to use it to get the calculated values that you need. Now that we've done a lot of applications of the derivative, coming up soon we're going to learn a little bit about the antiderivative. But until we get to that example video, continue on to the next. And until then, good luck with your online learning.